We want to look at this question related to Bayes' theorem. So this is exercise 3.85, which talks about how this corporation ships large consignments of light bulbs to big industrial users. And then it tells that when the production process is functioning correctly, which is 90% of the time, 10% of all bulbs produced are defective. How the process is susceptible to occasional malfunction, leading to a defective rate of 50%. Then it says that if a defective bulb is found, what is the probability that the process is functioning correctly? So the first thing that we're going to do is we're going to define some events over here. So we're going to define C to be the event that production process is functioning correctly. Is functioning correctly. And we're going to define D to be bulb produced is defective. Now we're going to write down, so after we've defined the events, we're going to write down the probabilities given to us. That's the next step that we're going to do. Now we are told that, now notice over here, we're told that probability that the production process is functioning correctly is 0.9. Now where is this given to us? This is given over here, right? When the production process is functioning correctly, which is 90% of the time. So this is this probability, right? So the probability of C, right? So let's look at the next probability that is given to us. And then we're told the probability, so then we're told the probability of defective given that the process is functioning correctly is 0.1. Now let's see where is this given to us. This, right, 10%, right? So when the production process is functioning correctly, which is 90% of the time, tells us that the probability that's functioning correctly is 0.9. But if you just ignore this, which is 90% of the time, and read it, when the production process is functioning correctly, 10% of all bulbs produced are defective, right? So this is essentially telling us that given that the production process is functioning correctly, the probability the bulb is defective is 0.9, right? 0.1, sorry. So if we look at the next probability that is given to us is probability D given C complement, which is 0.5. Where is this given to us? This is over here. Here it says, however, the process is susceptible to an occasional malfunction leading to a defective rate of 50%, right? This is the probability that it's defective given that it's not functioning correctly, given there's a malfunction. Right, so this is the probability defective given C complement, right? Now, next thing that you want to do is, so the first step was we defined our events, then we saw what probabilities were given to us. Now we want to use these probabilities to find, now we want to use the probabilities given to us to find other probabilities using the complement rule. I can say from here, we can infer that the probability the process is functioning correctly is 0.9. So the probability it's not functioning correctly, I see complement is 1 minus 0.9 is 0.1, right? Because it will either be functioning correctly or it won't be functioning correctly. Similarly, the probability that it's defective given correctly is 0.1. Okay. If it's functioning correctly, the probability defective is 0.1. So the probability that it's not defective given that it's functioning correctly is 1 minus 0.1 is 0.9. Similarly, the probability that it's defective given that it's not functioning correctly 0.5. So then the probability it's not effective given that it's not functioning correctly is 1 minus 0.5 is 0.5. Right, so first we defined our events, then we looked at what probabilities were given to us, and from there we found what probabilities can be inferred from using the complement rule, because it will either be functioning correctly or won't be functioning correctly. And given it's functioning correctly, it will either be defective or it won't be defective. Right? Given it's functioning correctly, it can be defective, it can't be defective. Similarly, given it's not functioning correctly, it can be defective, it cannot be defective. Something to note here, and just in passing, something, okay, so something to note here is going to be that probability A given B plus probability A prime given B is equal to 1, but probability A given B plus probability A given B prime is not necessarily equal to 1. Why? Because over here we're just we know the probability of A plus probability of A prime is 1, and this will hold true even if you're looking at a reduced sample space given B, right? So we know probability of A plus probability of A prime is 1, right? Both are complements, right? The union is the sample space of the whole idea, right? These are all the possibilities, right? You can either have A or then you have not A. So probability of A plus probability of A prime is 1. And this will also be true given the reduced sample space. But this is not true because here you're looking at two different sample spaces. Here you're looking at probability of A given B, and here you're looking at probability A given B prime, right? So there's no reason for this to be true. So this is for this. Now we can finally see what we want to find. So now we're told if a defective bulb is found, right? So our observation is defective bulb is found. Defective bulb is found. Now, where is this given to us in the question? Let's just look at that. Okay, we can use this, right? So the observation is this: if a defective bulb is found, right? So this is our so this is our observation if a defective bulb is found, right? And yeah. So now what we're going to do is, now what is required? What we are required to find is probability C given D, right? If a defective bulb is found, what is the probability the process is functioning correctly, right? So we want to find the probability it's functioning correctly given this observation the defective bulb is found. Now over here, the thing to note is we have P given D's. We have P, we have the probability of D given C, right? We're given this, right? 0.1. And you want its exact reverse, and want its exact reverse, so use Bayes theorem. Right, so why will we use Bayes theorem? Because we typically use Bayes theorem when we're given one form of conditional probability and we want to find its exact opposite. In this case, we're given the probability of D given C as 0.1 over here, and you want to find its exact opposite, so that's where we should use the Bayes rule. Just keep in mind, Bayes rule is used when you give one form conditional probability and you want to find its exact opposite. So, let's just uh, let's just keep this and let's just delete everything else. So we know we're gonna use Bayes rule now over here. Let's just let's keep this part and let's erase everything else. Just so we have more space to work with. Right, so we are going to now, so we want to find, like we said, probability of C given D. And if you apply Bayes rule, this will be probability D given C into probability of, probability of C. So if we're applying Bayes rule divided by probability of D. And when we're applying Bayes rule, we know the denominator comes from total of probability, comes from total law of probability, right? So probability of D. So in this case, we will find the probability defective by conditioning on the process is functioning correctly and the process not functioning correctly. So mutually exclusive collectively exhaustive events. So probability D would be probability it's defective given correct into probability of correct plus probability it's defective given it's not functioning correctly into the probability it's not functioning correctly. So now let's just plug in the numbers. Probability D given C is 0.1. Sorry, probability of C is 0.9, and then probability of D given C, like we said, is 0.1 into probability of C, which is 0.9, plus probability D given C prime is 0.5 into probability of C prime, which is 0.1. We found it over here, right? We deduced it using the complement rule, right? And then this just becomes basically, okay, so we did not. It's 4 point, no, it cannot be 4 point. Let's just see what this is. Just a sec. Let's see what this is. This is 0.1 into 0.9 divided by 0.1 into 0.9, and then it's plus 0.5 into 0.1. So this just turns out to be equal to 0.643. Okay, so now however, this was just one part. There's another part to this question. Let's do that. No. Oh no, we did not want to delete this. Let's just quickly erase this. And we're given the two essentially parts to this question. Let me just erase this, then we'll look at that. Let's keep this information because we need these probabilities. Yeah, so let me just make this probability. So there's another part to this part, right? If a non-defective bulb is found. So there are two parts to this question, right? So now the observation is non-defective bulb found, right? Non-defective bulb found. Let me just erase this a second. And where is this information given to us? Like we just saw. Okay, let's do this. A non-defective bulb is found. So this is this observation given to us, right? If a non-defective bulb is found, right? So what are we required to find? We are required to find probability. So what is the probability the process is operating correctly? So we want to find the probability of C given D prime. Now, if you notice again, we want to find, so the idea is this, if you notice, we have PD prime by C over here, right? And we have this by using the complement rule. Again, whenever you're given some probabilities, you can see using the complement rule, which probabilities can you find yourself from there, right? So we have probability D prime given C, which we found using the complement rule and want its exact reverse and want its exact reverse. So use Bayes theorem. So use Bayes theorem. Remember, we said we use Bayes theorem and we're given one for conditional probability. We're given probability D prime given C, and you want to find its exact opposite, probability of C prime given D. So now let's apply Bayes theorem here. Let me just delete this so we can apply it here. Right. So now let's apply Bayes theorem. We want to find probability C given D prime. So this would be probability D prime given C into probability of C divided by probability of D prime. And as mentioned before, the denominator comes from total law of probability. Denominator comes from total law of probability, where we can write probability as D prime. We're going to condition this on the process is correct. It's all good. Okay, it's actually, we could do this in two ways, probability of D prime. The two ways you could have done this, we could have done it by using total law probability, or okay, so first let's just do it from total law probability. Probability of D prime given C into probability of C plus probability of D prime given C prime into probability of C prime. Or note, probability it's not defective is 1 minus probability it's defective. We found this already, right? Found this when finding. So we found this when we were finding probability of C given D. Yes, typically when we're applying a Bayes rule, the denominator comes from total law probability. But in this case, since we already found probability of defective as the denominator of probability C given D, so we could have found probability of D prime is 1 minus probability of D, which we already found using total law probability. We could do it and either way, doesn't matter. So probability of D given C, we found this to be 0.9 using the complement rule. Probability of C is 0.9. And if we just apply the total law probability, then D prime given C is 0.9 into probability of C 0.9 plus probability of D prime given C, which is 0.9 into probability of C prime, which is 0.1. Right, and if you calculate this, this turns out to be 0.941. Right, so in this way we can apply Bayes theorem. Just keep in mind, Bayes theorem is used when you're given one form of conditional probability, like probability of A given B, and you want to find its exact opposite, right, probability of B given A. And typically the denominator will come from total law probability.